Hello everyone. So from today we are going to start our machine learning algorithms. As in my initial lectures, that is the introduction to machine learning, I told that in general we do divide machine learning into two categories, that is supervised learning and unsupervised learning. Supervised learning is a learning where you are available with a target, and unsupervised learning is a learning where we don't have a target. Okay, so if you consider a data set like this, if you are having a data, these are the features which are present in the data. Okay, and if you are available with y, that is your target variable or the target feature. So in this particular case, we are going to use supervised learning. However, if you don't have y, you are only having the features present in the data, not a target, then in that particular case, we'll be using unsupervised learning. Okay, fine. So both of them are different technique, different approach to make a machine learn. And in supervised, we have two types of learning, that is one is regression and another one is classification. Okay, regression and classification. So what are these two? See, regression and classification both are statistical techniques where you are trying to identify the relationship between x and y. However, in classification we will say that y is categorical in nature. In regression we say that y is continuous in nature. So both are statistical techniques, but the difference lies in the value of y. In case of regression, the value of y is continuous in nature. In case of classification, the value of y is categorical or discrete in nature. Okay, so ultimately, as I told, the data set itself says that in supervised that we are having x and y. So definitely, if you want a model to get learned over this particular data, ultimately the goal is to identify the relationship between x and y. Okay, so the relationship, if it's like regression analysis, that's I called as a regression analysis. So in regression analysis, the relationship we are looking forward between x and y is considered to be continuous in nature. For classification we say y is categorical or discrete in nature. Okay, so the simplest of all is a kind of a relationship between x and y is linear. We say that linear relationship is the simplest relationship between x and y. And an equation which we have studied in our maths also, that is y equal to mx plus c. Okay, so we are now focusing upon regression analysis. Classification we will see ahead. Okay. Currently, we are focusing upon regression analysis. As I told, regression, that is, you are looking forward to find the relationship between x and y. So, relationship can be linear in nature, a relationship can be non linear in nature. If the relationship is linear in nature, then you say it's a linear regression. That means it is following an base equation like y equal to mx plus c. M, you know that it is a slope, c is the intercept. Okay, fine. So that's a base equation. On this base equation, I can make a equation of simple linear regression as y equal to beta naught plus beta 1x plus epsilon. Epsilon is error term. Okay, this is error where beta naught and beta 1 are the coefficients, just like m and c. So you can say that beta 1 is a slope and beta naught is intercept. Okay, x is a variable, that is independent variable, and y is dependent variable. So right now we are finding the relationship between independent and dependent variable only. Why? What's the reason for doing this? See, if you are available with the data, again I am focusing upon data only. This is your data. Okay, and we are having features present in the data like x1, x2, x3, x4, x5. These are the features present in the data. Y is the target. So x1 till x5, these all are independent variables. Y is dependent variable. Dependent on whom? All these x. Okay, that's why we want to find the relationship between them. Okay, if I talk about this equation which I have written, simple linear regression. In simple linear regression, you are having one dependent and one independent only. That's what you are having. In simple linear regression, that's it. This is x, this is y. And the equation which you have written here, that this beta naught plus beta 1 x plus epsilon, that's the equation of simple linear regression only. That means you can plot it like this. This is x, this is y, and you can consider a straight line. And if you talk about the intercept, for example, there is an intercept, so you can start the line from here. This intercept is beta naught, and the slope is beta 1 tan theta. Slope is beta 1. Okay, so this is your y-axis, this is your x-axis, and the equation of the line is y equal to beta naught plus beta 1x. Okay, so that's a simple linear regression. We are trying to check the behavior. So you are in real world, so many data sets are there in which we try to find such kind of relationship between the variables. Okay, now let me share my entire screen to help you in better understanding. Okay, all right, so here it is. Fine. Okay, so you are writing y equal to beta naught plus beta 1x, introducing error term also. in the equation. This is the main part. Okay, in real world data set, it's not mandatory that you are having only one variable, one independent variable. No, you may have multiple independent variable. That's what I just made in the here in the diagram. You can see x1, x2, x4, x5. These are many independent variables, one dependent variable. That is why in this particular case you will say that my equation will become beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus epsilon, and it's called as multiple linear regression. Multiple linear regression, where again beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, these are coefficients. Okay, so beta 1, beta 2, beta 3, these can be considered a slope. Okay, and beta naught is your intercept. X1, x2, x3, x4, x5, these are the independent variables, and y is a dependent variable. Now I want to make you clear one thing, that if you make a data like this, 1, 2, 3, 4, so this is x1, x2, x3, x4, y. Every feature, now listen to me very carefully, every feature, every column, every dimension, whatever you want to say, you can, every variable represents a dimension. So if I 1, 2, 3, 4, 5, that means how many dimensions I am having? I am having six dimensions. I am having six dimensions. Okay. So this is 6D data. Every feature is considered to be as a one dimension. This is 6D data. And if you want to draw it, so it will be like this. Okay. It will be like this. This is 3D. This is 4D. This is 5D. This is 6D. Each and every line is perpendicular to each other. ये सब perpendicular है आपस में, perpendiculars. Every dimension is perpendicular to another dimension. So as you have studied so far, sir, 2D, you make 2D like this. Sir, this is x, this is y. This is 2D representation. You have studied 3D also. This is 3D when you include z axis. This is 3D. Okay. So now I am having a data with six features. So you can say that like x1, x2, x3, I can have many more, x4, x5. Okay, I can have a y. So every feature counts a dimension. Okay, why perpendicular? Why this Cartesian? We call as a Cartesian system. Na? Why? Because it is easier to interpret. Easier to interpret. As you are writing linear equation, no, no, y equal to mx plus c. That's what you're writing. Or you're saying beta naught plus beta 1 x. That's what you're writing. If let us suppose you are having x1, x2. Okay, so it can be drawn like this. Okay, it can be drawn like this: x1, x2, y, all are perpendicular to each other. Okay, these are the dimensions which are perpendicular to each other. Okay, so here you can have a point, like I can fill up the values like this. Okay, let us suppose x1, x2, y, 1, 1, 2. So you have to plot it. Okay, x1 ka okay 1, x2 ka bhi 1, y ka 2. So it will be like somewhere here in the space. So you can draw a vector 1, 1, 2. That's the reason we do study vectors and the matrices. So whatever be the entries which are present in the data, whatever be the entries which are present in the data, you can mark them in form of a vector. So for example, 1, 1, 2, 3, 4. Okay, so there could be a point here, 1, 1, 2, 3, 4. That can be marked with the help of a vector. So every entry can be written in a form of like this coordinate system, and they can be marked with the help of a vector. Okay, so we are simplifying the data in terms of this Cartesian coordinate system, and there are other coordinate system also. For example, polar coordinate, but they are complicated. We are not going to consider the complicated systems. We are going to consider the simple systems where I can represent the data easily and where I can mark the points easily. Okay, now one more question can come in your mind. You're saying, you can say that, sir, okay, we are having like so many variables independent. You are considering their slope as beta 1, beta 2, but why you are considering only one intercept? If there are many slopes corresponding to the independent variables, here you are written beta 1, beta 2. If you are having more, then still you will write like beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. But still you are writing only single intercept. Why you are not writing y equal to beta 1 plus beta 1 x1, beta 2 plus beta 2 x2, बीटा थ्री प्लस बीटा थ्री एक्स थ्री? तो सर सभी का स्लोप और इंटरसेप्ट आना चाहिए ना सर, सभी का आना चाहिए फॉर एवरी वन. But you are just only writing only beta naught and rest you are writing it with a slope. So the answer to this question is for simplicity. Okay, we don't want to make the things complex. Okay, we can have these terms beta 1, beta 2, beta 3 corresponding to what your independent variables are, but intercept will only be one, that is beta naught. Introducing more intercept will make your equation much more complex, because at the end, ultimately you have to find the value of the coefficients only. Coefficients value only you have to calculate. Now again there is a question, sir, why you are saying coefficient value we have to calculate? The point is very clear. In your data you are already available with x and y. All the value of x and y is available in your data. So what you are going to calculate then? Obviously, you have to look out for the coefficients value. And once you got the coefficient value, the next time you can ask your model to give the prediction. Okay, and the knowing coefficient value only, solving for finding the coefficient value for the best possible coefficient value, that is called as model training. That is only called as model training. Okay, so what you understood so far is, okay, sir, you are saying that currently we are studying regression. Okay, got it. In regression, sir, you are saying that we need to find the relationship between x and y. Okay, understood. X is independent, y is dependent. Understood. Okay, all these things are fine. Then you are saying that we can represent it in the form of like this beta naught plus b1x, either, or we can represent it in the form of beta naught plus b1 x1, and so on, depending upon whether you are using simple linear regression, whether you are using multiple linear regression according to the data set. Okay, you said beta naught, beta 1, all these are coefficients. Okay, that's what you said. And x and y are the variable that we know. Okay, and we are focusing upon linear relationship only, because if you write like this, y equal to beta naught plus beta 1 x square, this is polynomial relationship. Actually, polynomial we will study ahead. Right now we are focusing upon linear relationship. Okay, for example, if you are available with the data like this, okay, experience and salary, so it can be considered under simple linear regression. X is experience, y is salary. So we can expect here that experience and salary can have a linear relationship. As much as experience is increasing, salary is also increasing. We can say it's a simple regression analysis. Okay, we can have multiple regression analysis also. So many features if are available. Fine. Now, well, this is linear regression, a model to find relationship between x and y, which are assumed to be linearly related. Okay, that's an assumption. That means x is directly proportional to y, and not fully, not fully. Like, it can be like 80%, 90, whatever. Assumed to be linear relationship. Okay, that's the first assumption. Before using a model, before using linear regression, that is the first assumption. Mark it as a star, that x and y are linearly related. Okay, that is the assumption. Second is very important, normal distribution. What is normal? Like this. This is normal distribution. I already explained where mean, median, mode are equal. Mean, median, mode are equal. That is normal distribution. So in linear regression, we assume that continuous features should be normally distributed, where mean, median, mode are equal. See, what's the reason? Why you're saying that they should be normally distributed? If they are not normally distributed, then they will be skewed. Either there will be a long tail on the right, either there will be long tail on the left. Then it's a skewed data. And skewed is affected by the presence of outliers in the data. Skewed means outlier present either on the left side, either on the right side. What are outliers? Outliers are the wrong or faulty entries present in the data that are assumed to be, according to the statistical analysis, they are wrong or faulty entries present in the data. So, if you are having outliers, if your data is skewed, definitely it is impacting your regression analysis. Okay, it is impacting your regression analysis. So, your answer will be deviated to a certain set of values. If the orientation is normal, then I can have a proper result. As if the data is skewed, then according to the distribution of the data, your output will be impacted because of skewness. This is second assumption. Then the third assumption is there should be no multicollinearity, or I could either say no or very less correlation among the feature. That means if I am having x1, x2, x3, x4, x5, these are the features present in the data. There should not be multi-collinearity. Collinearity means the point should not come in a same line. Okay, the point should not come in a same line. Okay, like, okay, um, points of x1 and x2, if they come in a same line, then they are correlated with each other. I don't want the correlation. I don't want multi-collinearity, because if they are correlated, means x1 is increasing, x2 will also increase, or x1 is decreasing, x2 may also decrease. This is correlation, positive correlation. Either I would say it's a positive correlation. It may also happen that x1 is increasing, x2 may decrease with the same rate. Or it may happen that x1 is decreasing, x2 may increase with the same rate. This is negative correlation. So points should not come in a same line, in a single line, same one. Like, okay, this is collinearity, collinear. Also, there should be either very least or no correlation among the feature. These terms are related, collinearity and correlation. Okay, we don't want the features should be follow this criteria. We want them to be independent. That is the assumption, that all the features x1, x2, x3 all should be independent, but they should be in relation with y, linear. तो आपस में कोई रिश्तेदारी नहीं. There should not be any relation among themselves. हाँ, टारगेट से रिश्तेदारी. There should be relationship with the target, वो भी linear वाली. That is the assumption. These are the major assumptions, main assumptions. If you your data follow this assumption, then you can apply linear regression, else not. If you apply, your model will fail, your algorithm will fail. Okay, you'll not get the proper result. These are the basic assumptions. There are some more assumptions. Okay, that I will tell ahead. There are some more assumptions. Okay, but these are the major ones which we do check. Okay, fine. And then only we apply linear regression. Okay, so linear regression, this algorithm, this model is present in from sklearn, this library dot linear model. Import linear regression. Linear regression. Okay, linear regression. So in sklearn is the base library. In sklearn, I am having one folder that is linear model, and in linear model, I am having linear regression. So we can import linear regression from in this way. Okay, fine. Assumptions are very much important. If you don't follow the assumption, because every model, see, machine learning model are statistical models. Remember, statistical model. Statistical model means these are algorithms or techniques or equation based which follow statistics. Okay, statistics. And statistics, you already know that one is your inferential, one is descriptive. So, in both the cases, we are going to talk about the data. And unless and until your data is not proper, how you can apply statistics over it? Okay, so we have to perform statistical analysis, and according to the statistical analysis, we follow the assumptions, like assumption number one, that x and y are linearly dependent, then normally distributed, normal distribution. That means in your data, if you are having continuous features like which can be represented in an interval, they should be normally distributed. This is second assumption. Third is no correlation, no or less correlation among features. Among features, these are third. This is third. There are certain more. Right now, there's no sense of talking about them, but these three are mandatory to follow. Mandatory requirement. Once you refine your data in this particular way, then you can put in your model for training purpose. Then you can give it to the model for the training. Before that, if you give, fail. Result will not come. Every machine learning model do have expectations, assumption. Every model is having assumption. If you follow the assumption, then give it to the model. If you don't follow the assumption, fail. Okay. So why we are using this linear regression model? What is the goal of LR model? What is the goal of this? See, the goal of linear regression model is to find best fit line. Best fit line. That's what I want to find. Best fit line. Now, what is the best fit line? What are you talking about? It has been clearly told that relationship between x and y should be linear. Okay. In prediction, that means You do have a data X and Y. You split your data into training and testing. That means you take training data and the testing data. You split your data into training and testing. You train your model with the training data, then you test your data with that particular model, and you get the predictions. The expected is the expected is your predictions should be either on the best fit line or very closer to best fit line. Okay, for example, you got these as predicted points. Okay, these as predicted points. This is my best fit line. That means actual are present here, and these are the predictions. Okay, so if we find the distance of points from the line, they are called as errors. So this is E1, this is E2, this is E3, this is E4, and this is 0, because this point is on the line. What we want is the best fit line. Line means every point of predicted, every predicted point should come on the best fit line. Okay, but getting best fit is something like this is expectation. However, we can have a good fit. That means some points can come over a line, some can be nearby to the line. That is a good fit. We expect good fit. Okay, in our analysis, if we get the good fit, we agree with that. Getting best fit is something like it may happen you are having overfitting issues, but good fit it's justifiable. Okay, so these are the errors: E1, E2, E3, E4. Okay, now you can see that some errors are above the line, some errors are below the line, and these are the predicted points. These are the predicted points which a model predicted. Once it got trained, then it gave a prediction, and then there are errors. That means they are not coming on the line, they are coming either on above the line, either they are coming below the line. Some points may come over the line, that's not an issue. They are captured. That means they are captured. Okay, so we do have very important thing in analysis is error. Let us suppose y dash is predicted value and y is the actual value. So error is this thing only, no? See what you do have in AI. What you're trying to build a model which should give a prediction or the outputs like us. Okay, like us. So if the model gave output y dash and the actual output was y, so there is an error. There is a mistake which model did. So that mistake we are saying as y dash minus y. Okay, that's what we did. Okay, fine. So this error term is very much important, and the entire maths is dependent on error only. Either you do machine learning, either you do deep learning, or either you do generative AI. Error. The only task for us is to optimize the error. Optimize error. That means to reduce error and try to increase the score of prediction. That's what we want. The entire maths, everything is depend upon this thing only, to improve the scores, to reduce the error. If your model's error is reduced, that means its prediction is better. Its prediction is better, that means it is giving the good results. And that's what we are expecting from the model. Okay. So this will be the maths which we are going to apply. This is the maths which we are going to learn here. Okay. In case of currently, right now, we are dealing with linear regression. So that's what we are going to perform. Okay. Fine. So in the upcoming lecture, I will be talking about this error only. Okay, fine. So let me stop presenting now. Okay, let me stop recording.